Well, hello and welcome to online lecture 2A here in your Biology 111 semester. This is a very important online lecture. It's very important because it's hard just to understand all this atomic structure, the periodic table, all this chemistry stuff just by reading the book. So I think the explanations in this online lecture will really help you students as you're working through this course. We will be covering slides 11 through 25. So this is online lecture 2A covering slides 11 through 25. And our topics are a continuation of atomic structure. So we've already covered a little bit on protons in class. We've talked about neutrons some. And now we're really going to talk about the electrons and where they are located and how they are configured in the atom. And then we'll get into the periodic table. We'll talk about atomic mass, Avogadro's number, the mole, the concept of the mole, radioisotopes, lots of different things. Very foundational information. All this chemistry information is very key to understanding how life works. And so understanding chemistry and even physics is very helpful here in biology. So this foundational chapter is very important, guys. Just want you to know that. Of course, in today's online lecture, we'll also cover information related to the test to make sure you are aware of what kinds of things you might see on the test, and little tips along the way. And I just hope more than anything that the teaching is clear, that you really get what I'm trying to explain and what the book is trying to convey. So let's go ahead and look at this first slide, slide 11. So talking about electron shells. So when we talk about electron shells, we're talking about areas and sort of distances that are in places that are greater and greater from the center of the nucleus. So the shells are progressively at greater and greater distances from the center of the nucleus, and the shell itself is just an area of space. Okay, so it's just an area of space that is going to surround the nucleus. And the first shell, you would guess, would be very close to the nucleus. And so the electrons exist within these shells. These shells, these areas of space that are at greater and greater distances from the center of the nucleus. And within the shells, we have the orbitals. Okay, and what in the world is an orbital? Well, the orbital is sort of like the electron's room. Okay, so the orbital is where you are most likely to find an electron. And these orbitals are found within the shells. So you might think of the shell as kind of like being almost like maybe like the whole atom is like a house, and then the shells are like the floors in the house, so like the first floor, and then the orbitals would be like the rooms within the floors, right? Okay, so again, the atom is like the whole house, the shells are like the floors in the house, and then the orbitals are like the rooms within the floors. Okay, so let's look at the first shell. So in the first shell, which is what again? What is that in our analogy or metaphor? The first shell would be, that's right, your first floor. And within your first floor, there is actually only one room, and it's called the 1s orbital. So there's just one little room in the first floor, and that's true for all of the atom houses. Okay, so for every atom, remember atoms are like houses, they all have at least one shell, and within that one shell, that first floor, they all have this one room called the 1s orbital. Okay, so almost picture like a little room with 1s on the door leading into that room there on the first floor. And the reason it's called 1s is the 1 tells you it is what? The 1 tells you it's on the first floor. That's right, you're following just fine. And the s tells you that you are dealing with an s orbital. An s orbital. Now, what is that? An s orbital is simply a spherical orbital. All right, so it's just the shape. So the s orbital, any kind of s orbital, happens to have a spherical shape. All right, and the orbitals, and this is true for all of them, they all hold only one pair of electrons. So every orbital can hold how many? Yes, 2 electrons per orbital. Doesn't matter what kind of orbital it is, all orbitals hold only 2 electrons or one pair. All right, so we've explored the first floor. We now kind of understand how the electrons are arranged in the first shell or the first floor, and we've looked at the 1s orbital. Now let's go to the second floor, and this is the second shell, and this is true for all atoms that have a second shell. They have a spherical orbital up there on the second floor. So here on the second shell of the atom house, we have this spherical orbital called the 2s orbital. Remember, the 2 tells us it's what? The 2 tells us this orbital is in the second shell or on the second floor. And the s, what does that tell us? That's right, this room, this orbital is spherical. And how many electrons are found within this one orbital? That's right, guys, 2, right? Each orbital holds 2 electrons. So that's the 2s orbital. And that is just one of 4 rooms on the second shell. So what about the other 3 rooms, 3 orbitals here in the second shell? Well, there are 3 p orbitals. And the p orbitals have a dumbbell or propeller shape. So think of the p as standing for propeller. Of course, you know the 2 stands for the second floor or the second shell. So we have 3 p orbitals on the second shell. And each of those orbitals holds how many electrons? You guys remember? Each orbital holds 2 electrons, and there are 3 of them though. So 3 times 2, as you know, is 6. And so there are 6 total electrons there in the 3p orbitals. But remember too that we had 2 electrons in the 2s orbital. So how many total electrons can the second shell or floor hold? That's right, 8 electrons. Good job. I'll give you a smiley face for that one. So you're adding the 2 electrons in the 2s orbital plus the 3 2p orbitals there, right, which is a total of 6 potential electrons. Add that up, that's 8. So the second shell can hold up to 8 electrons, okay? So now you understand the first and second shells. We really won't get into the third shell. I'll just briefly mention this one, but the third shell has a 3s orbital. It also has 3 p orbitals, and it also even has 5 d orbitals. So the third shell can hold 18 electrons. But for our purposes in this course, you really aren't going to be tested on atoms that have more than 2 shells. In fact, most of the atoms that are important to the living world here in biology only have 2 shells. Okay? All right, so you get spared there. I'm sure you're breathing a sigh of relief not having to worry about the third or the fourth shell where we have 7 f orbitals. Wow, it gets crazy. All right, so let's get on to nitrogen now to bring it home. So at this point, you're probably thinking, all right, Mr. Spath, I need an example. Yes, so let's look at nitrogen. All right, nitrogen has 7 protons and 7 electrons. In case you're wondering, how do I know that? Well, you don't have to memorize that. You can use the periodic table on the test. And a periodic table will tell you how many protons and electrons are in a nitrogen atom, because next to the letter N, which stands for nitrogen, there's a big 7, and that 7 is called the atomic number, and that number tells you how many protons, which is normally equal to the number of electrons, is. So how are the electrons arranged in the nitrogen atom? So let's figure out where all 7 are arranged. Well, remember, nitrogen is like a house, right? So picture the nitrogen house. Here, I'll draw a little simple house here for you. And so here's the nitrogen house. We'll put a big N on the top for nitrogen. And we know this house has how many floors? Well, it just has 2 floors. And we know that because there are only 7 electrons that we have to put into this house. And 2 shells or 2 floors will be plenty enough to hold all 7. So let's look at the first floor of the nitrogen house. So on the first floor, what do we find here? In the first floor, the first shell, we have how many orbitals? That's right, there is only one s orbital found there, and it's called the 1s orbital. And it's what shape? That's right, it's spherical. And how many electrons can we put there in that 1s orbital? That's right, 2. So I'm going to put a 2 right there on the first floor, so you can see that that's all that the first floor can hold. So the electrons will go and fit into that 1s orbital. Now, we've only accounted for 2 electrons so far, but how many total electrons were there? That's right, there are 7 total. So how many do we have left? There we go, we have 5. So we have 5 more electrons, and they are going to go in the second shell, the second floor. So let's go upstairs, let's climb the stairs now, and we get to the second floor, and there are 4 rooms. There is one 2s orbital, right? And 2 electrons will automatically go in there. That's one of the rules of the house. The electrons always occupy the s orbital first. So the next 2 electrons will go into the 2s orbital. So there's 2 more electrons there. All right, so we've accounted for 4 electrons now, but there are 3 more. So how do the remaining 3 electrons go in to the second floor? Well, each of them will go into their own 3p orbital. So the 3 remaining electrons, because remember, 2 are in the first floor, 2 go into the 2s orbital there on the second shell. Well, there are 3 more electrons, and they each get to go in their own individual rooms. Now, you might be wondering, why is that, Mr. Spath? Why don't we have them, buddy up and pack them into maybe just 2 rooms? Well, it's because electrons repel. Electrons all have what charge? That's right, electrons have a negative charge. And do light charges attract or repel? Oh, that's right, light charges repel. So electrons would prefer, if they can, to be spread out in their own individual orbital. So there will be 1 electron in the remaining 3, in each of the remaining 3p orbitals. So we wind up with 5 electrons on the second shell, second floor, 2 electrons on the first shell or floor. That accounts for all 7. Note that the second shell is not entirely full. There are some spaces, aren't there, guys? Well, yeah, there's actually how many? Well, let's see if you've been paying attention. So how many electrons can the second floor hold? Can the second shell hold? That's right, the second shell can hold 8, but there are only 5 up there. So how many vacancies are there? How many openings are there? That's right, there are 3 openings. You see? So the might want to just note this, but the number, or I should say the electrons in the upper floor, whatever your upper floor happens to be, those electrons are called valence electrons. So for nitrogen, how many valence electrons are there? That's right, for nitrogen there are 5 valence electrons. So again, valence electrons just means the number of electrons in the outermost shell or the uppermost floor. So if we had an atom that had 3 floors and we had 2 electrons in the third floor, then that atom would have 2 valence electrons. Some atoms only have 1 shell, and so that's their upper floor, right? That's their highest floor. They just have 1. So for something like hydrogen, there is only 1 electron in its first shell, and so it has 1 valence electron. And that just happens to be the case for hydrogen. It just has a single floor. So does helium, but all other atoms have 2 or more floors. All right, guys. So hopefully this is coming together. I know it would be nice to have something more visual, so we'll be getting to that in just a minute. Let's see if we can find, here we go. Here's a nice visual. We got a nice picture here, and this will show you a nitrogen atom. As you can see here in the center, if you count up the number of protons, these are the red spheres. I'm circling those. So we have 1, 2, 3, 4, 5, 6, 7 red spherical protons. So there are 7 protons in here. There's probably just about that many neutrons because most nitrogen atoms have a mass of about 14, and that's typically the number of protons plus the number of neutrons. And of course, the number of electrons should equal the number of protons. Do you remember that? The number of electrons should equal the number of protons because the overall charge of the atom is neutral. And so we want to get the 7 positive charges of the protons to cancel out the 7 negative charges of the electrons. So we have 7 electrons. And again, there's the first 2 on the first shell. And they are in the what orbital? Ah, they are both in the 1s orbital. Correct. And then out here in the second shell, we have 2 electrons both packed into the what orbital? That's right, the 2s orbital. And then we have these 3 remaining electrons, and they are very happy. Why? Oh, don't you remember? The 3 remaining electrons are happy because they are all in their own room. Yes, they like that. Electrons repel, so they are just happy to have their own room. Gosh, wouldn't that be great at a university that you could just go off and have your own dorm room all to yourself, no roommate to worry about? Oh, I would have loved that. I had some horrible roommate situations, let's just say. Let's go up to slide 14 now. This is a more accurate depiction of the nitrogen atom. I'm not saying this is a perfect picture of a nitrogen atom. In fact, there's some flaws that we'll point out, but it's more accurate in the way the electrons are arranged. So here is the nitrogen atom. We have the nucleus right here. I'm circling it. It's just a sphere in the dead center, just a perfect sphere here, and it's way too what? Oh goodness, they made that thing way too big. In reality, the nucleus would be the size of like a tiny golf ball compared to a whole football stadium. So this nucleus, I'll put N for nucleus, is way too big. And then we can see the 1s orbital, and I'm going to circle that. The 1s orbital is just a larger sphere around the nucleus, and you can see the 2 electrons in it. And then we have the 3 p orbitals and the 2s orbital in the second shell. So I'm going to go ahead and just sort of draw out the border of the 2s orbital. So there's the 2s orbital with its 2 electrons. What about the 3p orbitals? Well, there's one right here going vertical, up and down. We have one that's kind of sort of sticking out of the screen and going back in the screen. Then we have another one that kind of runs horizontal. So there are 3 p orbitals on an x, a y, and a z axis. And that whole sort of thing there, completely combined there, is one nitrogen atom. Again, that's a more modern view of the atom because it shows everything in 3 dimensions. And you guessed it, orbitals are 3-dimensional. Right, guys? Okay, so let's now go a little bit more forward now to this topic of the protons. So we have so far in this online lecture looked at the arrangement of electrons in the atom. We've seen the electrons exist in shells, and more specifically in orbitals, and we've looked at the 1 and 2s, or I should say we've looked at the first and second shells, and we have looked at 1s, 2s, and even the 2p orbitals. So let's now move on to protons. Protons is really, the number of protons, I should say, is really what distinguishes one element from another, okay? So the protons give each atom their identity. So whether an atom is a gold atom or a silver atom or a hydrogen atom is all dependent on how many protons you have. So if you are an atom that has 6 protons, you are guaranteed to be a carbon atom. Yes, any atom that has 6 protons is a carbon atom, no exceptions. So that's what we mean by the number of protons distinguishes one element from another. And how can we figure out how many protons a particular atom has? Well, we look at the periodic table and we are given this thing called the atomic number. The atomic number, number 1, equals the number of protons, but it also is equal to the number of electrons in an atom, because atoms are electrically what? Atoms are electrically neutral, right? And since they are, the number of protons equals the number of electrons in a neutral atom. So when you're given the atomic number, you're actually given information about the number of protons and the number of electrons. So let's just test you really quickly. Let's say I have an atom that has an atomic number of 8. All right, so how many protons does that atom have? That's right, it's 8. And how many electrons does it have? That's right, it has 8 electrons also. So good to know that. And by the way, does anyone know what that is? An atom that has eight protons is oxygen. All right, good job. Hey, I'll give you another smiley face, right? Oh, oxygen. We'll make it like a happy oxygen. Why not? Okay, guys, let's move on now to the next one here. Periodic table. You might be thinking, okay, we just talked about the atomic number. Now it looks like we're changing topics, but we're actually not. The periodic table is a table of all of the elements, both naturally occurring and man-made. The first 92 elements are naturally occurring. Once we hit element number 93 and on up to, I think we're up to like 120 almost now, those are all man-made or human-made, right? And the periodic table is organized by atomic number. The rows in the periodic table tell you the number of electron shells. So if I have an atom in the 3rd row, how many shells does it have? That's right, 3 shells. That's simple. And we have columns in the periodic table. These are vertical, right? Rows are horizontal. Columns, vertical, which are from left to right across the table, but they are vertically arranged, indicate the numbers of electrons in the outer shell. And what is the number of electrons in the outer shell called? That's right, they're called valence electrons. So you don't even have to count it up, guys. You can just see what column the atom is in, and based on that, you can figure out the number of valence electrons. So let's say we had an atom in the 7th column in group 7A. So how many electrons, how many valence electrons would that atom have? That's right, 7. So the columns give us the number of outermost or valence electrons. The rows tell us the number of electron shells. Very, very good. And gosh, that's almost guaranteed to be on the test. So on the test, it might say an atom is in the 4th column and 3rd row. How many valence electrons and shells does it have? If it's in the 4th column and the 3rd row, it's going to have 4 valence electrons and 3 electron shells. Good job. All right, now there's a significance to what column the element is. It so happens that atoms that are in the same column, in the same vertical column, tend to have similar chemical properties. Why is that? Because they have the same number of valence electrons. The valence electrons help determine the type of chemical bonding properties that atom has. So, for example, all of the atoms in group 1 or column 1, which of course would have how many valence electrons? That's right, they would all have 1. they all happen to be rather chemically reactive. They tend to be kind of volatile or corrosive. Whereas the atoms in group 8 or column 8 tend to be very stable and non-reactive, non-explosive, rather stable. So the groups or columns are also called families because they all have similar properties, just like a lot of people in your family have similar properties or appearances, let's say. Okay, let's move on to this picture of the periodic table. So here is the periodic table. It is a simplified version of it. It shows you numbers 1 through 18. And you can see the rows and the columns. And I'm just going to, while we're here, why don't I ask you a question? All right, let's pick on aluminum. So let's see if you can find aluminum and see if you can tell me the number of protons aluminum has. You remember you have to find aluminum's atomic number. So aluminum has how many protons? Correct, 13. All right, so we know aluminum has 13 protons, so it must also have what? That's right, it must also have 13 electrons because it's electrically neutral, like all atoms are. And aluminum is in the third row and the third column. So how many valence electrons? 3. And you can see them. 1, 2, 3. And how many shells does it have? 3. 1, 2, 3, because it's in the third row. Try this for oxygen. See if you can tell me how many rows and columns and number of total electrons and protons. So oxygen is 8, so it has 8 protons and 8 electrons. It's in the second column, so it is, I should say, second row. And since it's in the second row, it has 2 shells, 1, 2. And since it's in the sixth column, it has how many valence electrons? 1, 2, 3, 4, 5, 6. All right, so I think we're getting it now, and it's really not going to be terribly hard. That's one good thing about with biology. We're not going to get into the super complex information of chemistry. Just rather simple here. All right, moving on now. Slide 18, atomic mass. All right, so we have to have a way of determining the amount of matter in each atom. So there are very massive atoms, and there are some atoms that have much less mass. So what determines the amount of atomic mass in a particular atom? Well, it's the number of protons and neutrons. Protons and neutrons are quite massive. They are 1,800 times the mass of an electron. You might say that electrons have extremely low mass. As a result, electrons are not included in the atomic mass calculation. We don't even consider them because they're so light and so with such little matter. So the number of protons plus the number of neutrons gives us the mass number. So if I had 5 protons and 4 neutrons, the mass number would be 9. And the mass number is very close to the atomic mass. The atomic mass is a little bit more precise than the mass number. Again, mass number is just protons plus neutrons. Atomic mass is going to be very precise, might include decimals. We'll talk about why that's the case in a little bit. So the atomic mass scale is all dependent on the atom's mass relative to the mass of other atoms. So this is a relative scale where we compare all atoms to one element. And that one element, guys, is carbon. Carbon has been assigned an atomic mass of exactly 12. And that is the standard by which we measure everything else. For example, hydrogen. Hydrogen has an atomic mass of 1. Why? Because it is 1/12 the mass of a carbon atom. You see, guys? So carbon is the standard. And since it has an atomic mass of 12, and hydrogen has 1/12 the mass of a carbon atom, we give hydrogen an atomic mass of exactly 1. Magnesium is double the atomic mass of carbon. So it has an atomic mass of 24, 12 times 2. You see? So atomic mass is completely based on the atom carbon. Let's go on to slide 13, or I should say 19, my bad. Looking at slide 19, we have atomic mass in relation to the mass of an electron. So you can see the protons and neutrons are both in the nucleus. As we know before, protons are positive charge, neutrons are neutral, no charge at all. And look at their mass relative to the electron, 1,800 times the mass of an electron. So neutrons, as you can see, are slightly more massive than protons. And then the electrons have very, very little mass. And they, of course, have a full negative charge. And they're not in the nucleus, they're located around the nucleus. Nice little summary there in that table. Let's move forward to slide 20 now. And while we're talking about mass, we should make sure that everyone understands there's a difference between mass and weight. All right, so mass, folks, is just the amount of matter in a substance, okay, or in an object. It's just the amount of matter, and it doesn't change from place to place. So whether you're here on Earth or whether you're on the moon, anywhere, your mass will not change unless on the way to the moon or someplace in the solar system or someplace in the universe you lose your arm or something. Well, then your mass would change. But assume your body remains intact, your mass will not vary from place to place. However, weight does change. Why? Because your weight is derived from the gravitational pull on a given mass. So weight is a force of gravity between you and whatever object you're standing on. So we're on the Earth, so we're experiencing a gravitational pull between us and Earth. That gives us our weight. So if you weigh 154 pounds on Earth, on the moon you would only weigh 25 pounds, which is about 1/6 of your weight. But on a neutron star, which is very massive, you would weigh 21 trillion pounds. Wow. But this person's mass would be the same in all locations. Remember, mass is the amount of matter. Weight is the gravitational pull, and that does vary from place to place. Okay? So just keep that in mind. You should be just fine on the test. Just make sure you understand mass versus weight. Okay? That's definitely going to show up. Let's go to units. So anytime we talk about mass or weight or any type of measurement, we need to talk a little bit about units. So the units of atomic mass in the chemical world is the Dalton, named after the person that basically discovered the existence of atoms. The English chemist John Dalton. He basically postulated that matter is composed of tiny individual units he called atoms. So he basically discovered atoms. Dalton is a measurement of atomic mass, as we said before. It's also called the atomic mass unit. And 1 Dalton is, you guessed it, 1/12 the mass of a carbon atom. So a hydrogen atom has a mass of just 1 Dalton, whereas the carbon atom has a mass of 12 Daltons. And magnesium would then have a mass of 24 Daltons. Okay, see, these are very, very tiny units. We don't typically use grams, which is a normal unit of mass, for atoms because atoms are so small. So it wouldn't make sense to use a gram. It's like trying to describe a person in terms of their weight in tons. That wouldn't really work too well. We'd all be point something tons. So instead we use pounds. Well, we use Daltons for atoms. Makes more sense. All right, while we're talking about that, we have the concept of the mole. All right, so if I said I had a dozen eggs, how many eggs do I have? That's right, guys, 12. 3 dozen eggs? That's right, 36 eggs. Okay, so in the atomic world, a dozen just doesn't cut it because there are so many atoms. Atoms are so small, they're so numerous. We can't use a dozen. We can't use a lot of other things that would describe a mass of something. So we came up with something called the mole. The mole is 6.022 times 10 to the 23rd of something. Okay, just like saying we have a dozen eggs, we have 6.022 times 10 to the 23rd atoms in a mole of atoms. So a mole is a massive number of atoms. It's incredible. That number is called Avogadro's number. Very important number to remember in chemistry in particular. So because atoms, again, are so numerous, we don't typically say we have, 10,000 atoms. No, we typically say, well, there's a mole of atoms or 2 moles of atoms. The mole is such a huge number, guys. It's so hard to imagine, but I like this description. So to understand a mole, imagine 1 million people moving through a turnstile every second. Okay, so 1 million people going through a turnstile every second. It would still take 20 billion years for a mole of people to get through. Wow. So it's just an astounding number. Our minds can't even comprehend it. Let's get on now to isotopes. So before we even do that, I just want to mention that when we talk about moles of something, if you did have a mole of a light element like hydrogen, hydrogen is incredibly light. If you remember, hydrogen has a mass of only 1 Dalton. So what would be the mass of a whole mole of hydrogen atoms? Well, that's a huge number, but it just so happens that a mass of a mole of hydrogen atoms is actually 1 gram. Okay? It just kind of works out that way. So if we have one individual hydrogen atom, that one would have a mass of 1 Dalton. But a mass of a mole of hydrogen would be 1 gram. Okay? All right, let's just try that for carbon. So if we have 1 carbon atom, do you remember? That has a mass of how many Daltons for 1 carbon atom? That's right, it's 12 Daltons. But what would be a mass of a whole mole of carbon atoms? It would be 12 grams. You see? Okay, so that's just kind of how it works out. So you can kind of see how the concept of the mole sort of helps us understand these great numbers of atoms, maybe. At least I hope that makes some sense. Isotopes. So we've talked about atomic masses, we've talked about elements. Now let's sort of look at this idea of the isotope, where you can have more forms of a particular element. So as we've just talked about these elements, carbon, hydrogen, nitrogen, oxygen, there are some variations within those isotopes, or I should say there are variations within each element, and those variations are called isotopes, where they differ in their numbers of neutrons. So isotopes are atoms of the same element that have different numbers of neutrons. Okay, there's your definition. Let's look at an example. So we have an isotope of carbon called carbon-12. Most carbon atoms have a mass of 12. And so most carbon atoms are C12. And we write the mass number to the left and above the chemical symbol. This carbon-12 is, again, 99% of the carbon atoms in nature. And that carbon-12 has 6 protons and 6 neutrons. Okay? So carbon-12, 6 protons, 6 neutrons, very common. 99% of the carbon atoms in nature are carbon-12. However, there's also another kind of carbon out there called carbon-14. Carbon-14, of course, has 6 protons. How do we know that? Well, remember, the number of protons gives each element their identity. So all carbon atoms have to have 6 protons. So what would make carbon-14 more massive than carbon-12? It has to be the neutrons. So carbon-14 has 8 neutrons. 8 plus 6, 14. Now only about 1% of the carbon atoms out there are carbon-14. Interesting thing that when you're trying to figure out the average atomic mass out there, you have to average out the masses of all the carbon-12s, let's say, and then you factor in the mass of the 1% out there, the carbon-14s. And when you do that, the average mass of a carbon atom is actually 12.011. And so you'll see that when you look at the atomic masses with their precision, they're always going to be a decimal because of the different isotopes of an element. So instead of the average mass of a carbon atom being exactly 12, like 12.00, it's actually 12.011 because the carbon 14s bump the average up slightly. Okay? And so atomic masses are averages of the weights of different isotopes of an element. So atomic masses almost always are going to have a decimal and then something else. Compare that, though, with the mass number. The mass number is basically the atomic mass rounded to the nearest ones. So again, with carbon, your atomic mass is 12.011. So the mass number would just be 12. Just the atomic mass rounded to the ones place. That's a pretty good rule of thumb here in chemistry. Okay, let's now go on to slide 23. You might be wondering, what in the world is this? Well, this demonstrates radioisotopes. Radioisotopes are isotopes of an element that are unstable, that actually emit radiation. So their nuclei, their nucleuses, break down spontaneously. They're unstable, and as they do so, they emit radiation. So you might think they're all bad, maybe, because radiation is typically bad. Yes, radiation can cause cancer and disruption of cell function and even death. But if you have small amounts of radioisotope, we can use that in modern medicine. For example, radioisotopes can be used to destroy cancer cells through their emission of high energy radiation. And they can be used to track a particular substance. So let me give you an example of that here. So this is a PET scan, PET, positron emission tomography. The PET scan is a way to track biologically important molecules. And in this particular PET scan, this person's being scanned for cancer, and we'll talk more about how that's done, but this person actually has lung cancer. Their brain is glowing, but that's because the brain is very metabolically active and there's a lot of glucose going to the brain, and so it shows up there. And then the bladder is very bright, as you can see down here at the lower part of the person's body. That's very bright because excess sugars can go through the urine, but all these bright spots in the lungs are not supposed to be there. Why is that? Well, cancerous cells have very high metabolism. They gobble up a lot of sugar, and as they gobble up a lot of sugar, they also take in a lot of this radioisotope and they wind up glowing. So the way this works is, in this particular case, glucose is C6H12O6. Okay, glucose is a sugar molecule that our body uses for just about everything. So a very important energy molecule. What we can do is we can take a radioisotope, fluorine-18. So fluorine-18 is a radioisotope of fluorine, and it can go into the glucose molecule and become a part of it. And thereby, we can now track the glucose molecule. We normally can't track glucose because it's not radioactive, but when we add fluorine to it, now everywhere the glucose goes, it will emit radiation and it will show up on a PET scan. So this person just gulped down some slightly radioactive glucose solution, which again is not harmful in low amounts, and then the glucose wound up going to places where cells are particularly metabolically active. So in the brain, and of course where all the cancerous cells are. If cancerous cells were not super metabolically active and didn't burn up a lot of sugar, this would not work. So the PET scan is amazing. 1 to 2 million PET scans are performed every year in America alone, and that helps save so many lives. So good practical application of radioisotopes in the real world. Okay guys, down to the last little part here, we're going to wrap up talking about all of the atoms that are important in the living world. So we've been talking about all these different atoms and different types of elements. which ones are the most important to us and what are the bodies that we have actually made of? Well, most of your body, 95% of the mass of your body is hydrogen, oxygen, carbon, and nitrogen. And I can give you a quick little word for that, CHON. C-H-O-N. Remember that on the test. CHON, 95% of your mass. You need to be able to recognize these four elements as being the most common in your body. We have a lot of hydrogen and oxygen. Why? Well, I bet you can guess. We have a lot of that because 60% of our body is water. So there's a lot of H and O. And there's, of course, a lot of carbon because we were made of proteins, carbs, lipids, nucleic acids. And then nitrogen is very common in our proteins. So we are mostly CHON. You can see down here the next biggest group are called the mineral elements. Mineral elements make up less than 1% of our mass, but they are very important. They actually help form our skeleton. Your skeleton is phosphorus and calcium. And phosphorus and calcium, of course, are mineral elements. And then in very small amounts, you have the trace elements, which make up less than 0.01%. And they are typically metals. All right? Trace elements are usually metals. Good to know that. They are very uncommon, only 0.01%, but they are essential. Don't think, well, I only have to have 0.01%. It's no big deal. I don't need them. You actually have to have them. A good example is iron. Fe, iron. You have to have iron for oxygen to attach to your red blood cells to be carried throughout your body. Without iron, you can become so anemic it could actually become deadly. So you have to have some iron, even though it's less than 0.01% of the mass of your body. Normal growth and function, you've got to have those. Mineral elements typically are found in groups 1, 2, 6, and 7 of the periodic table. That's one way you can remember that. And they also play a big role in the conduction of electrical impulses. So we'll get more into that later this semester. So here is a nice summary of all of the elements that make up living things. There's the big four, CHON, 95%. There are all of your mineral elements, calcium, chlorine, magnesium, phosphorus, potassium, sodium, sulfur. Again, pretty much in groups 1, 2, 6, and 7 on the periodic table. And then we have the trace elements, which are typically metals like chromium, copper, cobalt, iron, tin, zinc, and there's some others that are non-metals, but a lot of them are metals playing very essential roles, particularly in your metabolism, the chemistry of your body. So guys, this is wrapping up this online lecture 2A. We've covered a lot of material, very important information. I'm sure there are some questions you may have. This is definitely more difficult material. So I expect some questions in class, or you can always email me at mspath@wpcc.edu. Have a good day.